So now let's look at some more fundamental properties of Markov chains. And we're going to ask some questions. First, we're going to ask, can we say at the beginning of generating data from a Markov chain which state we're going to be in at time t+1? So we start at time 1 or time 0, however we index it, and then we start the Markov chain by generating data from a Markov transition matrix M. And we want to say, if I do that and go to step t+1, can I say where I'm going to be, what state I'm going to be in at t+1, at time t+1, before I even start this entire process? So we can do this. We can use basic probability calculations to find what this is. So let's imagine that first we're at step t. So we're imagining we're at step t right now. And we have a probability distribution. We already were able to somehow figure out, standing at time 1, what the probability distribution is of where I'm going to be at time t. Let's call that this p, this probability of being in state u at time t. So we're going to call it that probability this, and we're going to pretend like we know what this is. In that case, the distribution on where I'm at t+1, so if we want to find the probability that I'm in state j at time t+1, I simply write that as a marginal of a joint probability of being in state u at time t and in being in state j at time t+1, and now sum over all values for u to integrate or sum out this, this state variable at time t. So I represent this, this marginal probability as a marginalization of this joint probability, but then I take this joint and write it as a conditional times a prior. So I can write this joint probability as the probability, given that I'm in state u at time t, of transitioning from state u to state j at time t+1, times a prior probability of being in state u at time t to begin with. So I multiply these two things together, I sum over all of the states for time t, and I get my marginal distribution of where I'm at time t+1. So let's now change notation, just change the notation and let wt be a row vector of length s that gives me a probability distribution on the capital S different states at time t. So wt is my marginal probability of which of the capital S states I'm in at time t. Then we can say that this, this probability is the vector wt+1 evaluated at dimension j. We can say that this prior probability is the vector wt evaluated at dimension u. And now this probability of transitioning from state u to state j, because we're assuming that the probability is not changing with time, is simply the element, the ujth element in the Markov transition matrix M. So this probability we can read off by looking at the uth row and the jth column of the matrix M. And so now we have a vector matrix way of writing this, that at time t+1, my s-dimensional, capital S-dimensional row vector of the probability of where I'm at that time is equal to the same probability of where I'm at time, except at time t, times the matrix M. So that's what this sum is doing. It's taking this vector times this matrix. It's just two different ways, two different notations to represent the same thing. So we take the row vector wt, we multiply it by m, and we get the distribution at t+1. And so we have this iterative way. For example, we know that wt can be written as wt minus 1 times m. And if we keep stepping backwards, then once we arrive at the state that we're in at time 1, we can say that the state that I'm in at time t+1 is equal to the state that I'm in at time t, at time 1, times the transition matrix raised to the power t. And what this notation is saying is it's important to know, is not an element-wise exponential. So we don't take each element in m and raise it to the power t. We have m times m times m, and this happens t times. And so now if we know what state we're in at time 1, for example, we know where we're starting at time 1, we can let this vector w1 be a vector of all zeros except for a 1 placed in the dimension corresponding to the state we're in, which is simply another way of writing a probability on my state that I'm in now that is deterministic. If it's probability 1 of being where I'm at now, then it's a guaranteed thing. And so this vector will then pick out the correct row of this m raised to the t. And that will be this probability that I'm in state, any given state at time t plus 1, given that I'm in a particular state at time 1. So now we've given a way to represent my probability of where I'm at time t plus 1, given where I'm at, given my probability of where I'm at time t. It's simply this vector matrix product using the same Markov chain, and then we know how we can unpeel this to represent it as a starting vector times a power of m. The question is now, what's happening as t goes to infinity? Is anything interesting happening? Is it converging to anything important? So we're going to define this distribution, w infinity, which is the limit as t goes to infinity of wt. So this is the distribution on where I'm at an infinite number of steps from now. This w infinity has a name, and it's called the stationary distribution of a Markov chain, m. So the stationary distribution of the Markov chain m is equal to w infinity according to this notation. So there are many technical results that can be proven about this. We're just going to recite a couple of properties about this. So if the following two conditions are true, then the important thing to know is that this w infinity will be the same vector no matter where I start out. So given any state that I start out at, w infinity, my distribution on where I'm at an infinite number of steps from now is the same in all cases. So just telling me where I'm starting is not going to help me say anything about where I'm going in the infinite distance. But this is only true if first we can reach any state in the Markov chain by starting from any other state. So that says that if I start in a particular state and then I transition according to the Markov transition matrix M, at some point I can eventually reach any other state, no matter where I start. Also, the sequence can't have any sort of hidden loops where we're converging between states in some deterministic way. So there can't be any sort of deterministic convergings for transitions. For example, I always transition. For example, I have a state like this, 3 states like this, and I always transition like this between these 3 states in a deterministic loop. We can't have anything like that encoded in M. In those 2 cases, if those are true, then no matter where we start, we're going to converge to the same stationary distribution. We're going to have the same uncertainty or the same level of belief of where we're going to be an infinite number of steps from now, no matter where we start. So if we have converged to a stationary distribution, and we've shown that we have this sort of a representation where wt plus 1 is equal to wt times m, and wt is converging as t goes to infinity to a vector called the stationary distribution. What that means is that w infinity is a vector that has this property where if we take w infinity times m, we get w infinity back. So we're looking for a vector having this property to be our stationary vector. And this is closely related to the eigenvectors of the transpose of the Markov transition matrix. So remember that q1 and lambda 1 are the first eigenvector and eigenvalue of a matrix M transpose if M transpose q1 is equal to lambda 1 q1. So this is the property of an eigenvalue and an eigenvector And the first one is the maximum value for lambda 1. So there would, in general, be many of these pairs, but the first one is the one corresponding to the maximum value for lambda. And so it can be shown that for this specific matrix, if we have a Markov transition matrix, if we have a matrix M such that all the values are non-negative and all the rows sum to 1, then the first eigenvalue of the transpose of that matrix is equal to 1. And the first eigenvector relates to the stationary distribution in this way. So remember, by definition, the eigenvector has to have an L2 norm of 1. And so we can get the stationary distribution, which has an L1 norm equal to 1. So we square Q1, we square them, sum them up, that equals 1. With this W infinity, we want to sum them up without squaring them, then have that equal to 1. We can recover the stationary distribution by taking the first eigenvector of M transpose and normalizing it. And so there's a clear relationship between eigenvectors of this matrix and the stationary distribution. So in practice, what that means is that when we want to know what this stationary distribution is, we don't simply keep multiplying M by itself until we hopefully get close enough to some level of convergence. What we can do is take the transpose of M and call a built-in function to find its first eigenvector, and then perform a simple normalizing of that eigenvector to get the stationary distribution.